Hey everyone, welcome to The Explainer. I'm absolutely thrilled to have you here today because we're unpacking a massive geopolitical catalyst that is quite literally breaking standard automated routing pipelines all over the world. We're going to look really closely at the Hormuz routing anomaly and break down exactly how developers need to fix their logistics APIs after the Everlovely incident. Here's our roadmap for today. We'll start with the Everlovely incident, move into why routing algorithms are breaking, figure out how to fix those AIS data pipelines, look at risk-weighted ETA models, and finish up with a concrete developer action plan. All right, let's dive right into Section 1, the Everlovely incident. So, to set the scene, before all this kicked off, the Strait of Hormuz was seeing a steady flow of about 130 to 150 vessels transiting every single day. But suddenly, traffic plummeted by 30 to 40%. In one recent 24-hour window, only 78 ships actually made the transit. Now, you might just be thinking, okay, physical bottleneck, right? Well, yes, but for us, it represents a massive sudden drop in the typical data volume hitting our API endpoints. And that data drought immediately throws predictive models completely out of sync. Let's walk through exactly how fast this happened. It started with a US-Iran interim deal, which actually prompted Western navies to recommend taking the southern route. But then on June 25th, a container ship called the Everlovely took a projectile hit right on that recommended route. This forced the International Maritime Organization, the IMO, to immediately suspend their ongoing evacuation plans in the strait. But here's the kicker. Vessel traffic kept adapting, in real time right through late June. The physical landscape shifted practically overnight, leaving static routing engines completely scrambling to keep up. And, this quote really puts the human scale of this logistical event into perspective. IMO Secretary General Arsenio Dominguez noted that they managed to evacuate around 115 vessels, meaning about 2,500 seafarers safely left before they had to pause operations for safety guarantees. So why does this matter for your software architecture? Because this kind of massive logistical undertaking introduces purely human-driven variables. We're talking manual holding patterns, sudden course corrections, massive queue delays, stuff that rigid, static algorithms absolutely cannot process. Which brings us to Section 2, broken routing algorithms. Let's look at a few specific ships to see exactly why our tracking systems are having a total meltdown. Take the Bannistar and the Blue Star Eye. Both of these ships executed sudden tactical U-turns after getting radio warnings from the IRGC, but then they just resumed the southern route a few hours later. Or look at the SG Pegasus. It completely bailed on the southern Omani corridor and switched to the northern Iranian route mid-voyage. These are complex, real-time human overrides executed by ship captains trying to stay safe, and they are completely baffling standard predictive routing systems. And here is where the tech breaks down. Your standard API parsers, they look at these sudden tactical U-turns and assume, oh, dropped signal or navigation error. And then what happens? They often drop the record entirely. Poof, gone. It completely corrupts the data pipeline. But if you switch to dynamic AIS parsers, you can update your anomaly detection logic to actually log a U-turn as a dynamic route adjustment event. It's a small tweak, but it literally saves the pipeline. Okay, let's get into fixing things. Section 3, fixing AIS data pipelines. First rule of thumb right now. Please stop tracking by vessel names. When you have a high-traffic anomaly like this, you've got multiple vessels sharing similar designations across different registries. It causes absolutely massive name collisions in your database. You've got to preserve the original IMO number as your primary key. Also, make sure you're pulling deadweight tonnage, IMO, and route type directly from high-fidelity feeds like Lloyd's List Intelligence. Oh, and a quick pro tip, cache those responses with a 10-minute time to live. Trust me, you do not want to hit rate limits when these routing events suddenly spike. And this leads us to the big architectural shift we desperately need right now, state machines. You see, legacy systems tend to throw a complete tantrum the second a ship turns around. Instead of a linear tracker, a state machine is a dynamic tracking model. It actually recognizes a tactical vessel reversal, followed by a route resumption, instead of just crying, signal loss. By upgrading to this model, you're ensuring that legitimate evasive maneuvers in a conflict zone don't absolutely nuke your logistics database. Moving right along to Section 4, risk-weighted ETA models. Listen, those pre-war baselines you relied on, they're useless now. We have to start multiplying base ETAs using real-time conditions. So let's say an IRGC warning pops up on the southern route, your system needs to instantly apply a 1.2 latency multiplier to the base ETA. If the IMO evacuation process is active, add 0.15 to account for massive queue delays. If a ship takes the northern route, add zero point 0.1 for the higher baseline congestion. You are essentially coding real-world geopolitical frictions straight into your routing optimizers. And hey, remember, it's not just about time latency anymore. These new ETA cost functions have to juggle a bunch of dynamic variables. We're talking real-time flags from UK maritime trade operations, sudden queue delays from IMO exit operations, and crucially, surging insurance war risk premiums. Your routing optimizer has to weigh financial risk and toll parameter shifts just as heavily as physical transit time. Because sure, a route might be miles shorter, but if the war risk surcharge makes it financially unviable, your algorithm needs to know that before it spits out a recommendation.
Finally, let's wrap this up with Section 5, Developer Action Plan.
All right, if you're the one keeping these systems afloat, here's your rapid response action plan. Step 1, pin your AIS data providers. Stop using generic API feeds and switch to robust providers like Lloyd's List Intelligence that won't drop records during route switches. Step 2, audit your SLA delivery contracts, like right now. If your platform is guaranteeing delivery windows based on a pre-war 13-vessel-a-day baseline, you are definitely going to miss your targets. Step 3, test your routing engine against historical AIS dumps specifically from that June 23rd to 26 anomaly window. Make sure those tactical U-turns process correctly. And Step 4, closely monitor IMO evacuation metrics. Flag any vessel over 10,000 deadweight tonnage in the Gulf for manual review until things stabilize. As we wrap up this explainer, I want to leave you with a bit of a provocative question to chew on. Will static logistics algorithms ever be reliable again in such a volatile geopolitical landscape? The maritime tracking data we've dug into today pretty heavily suggests that the old set-it-and-forget-it days of routing, they're over. We're entering an era of dynamic, risk-weighted systems that have to constantly ingest real-world chaos. The physical world is unpredictable, and our software architecture absolutely must evolve to match it. Thanks so much for learning with me today. Now go patch those data pipelines, and I'll catch you in the next explainer.